In this video, I want to cover the topic of spaces in Nodal. An awful lot of the time, making sure that you are doing things in the correct space will be fundamentally important to getting the right output that you require. Also, of course, knowing what space you're in and understanding the whole concept of spaces themselves will be necessary for you to understand the flow of information properly. Space, positions, orientations are important to Nodal because they're fundamentally important to Lightwave itself. As such, if you want to make sure that you're completely up to speed on them, then you should check out my YouTube channel and the Rigging Primer playlist, and have yourself a watch of the videos on space and rotation and orientation. So assuming you're familiar with those basic ideas and concepts, let's talk about how they come into play in the node editor. First of all, you have two space constants to consider in any network, and that is the source space and the destination space. So for instance, you take an item's information here. You can be looking at its position, which is of course its keyed value position relative to its parent space. Of course you have its world position, which is its position in world coordinates. These are examples of source spaces available from something. Your target space, or destination space, is always, of course, that space that essentially the destination node is in. Here, in the surface editor, your destination is always object space. That object space may be viewed in different ways, such as the x, y, z of its local space, or perhaps its u and v, if it has a UV map, or even potentially the UV values of individual polygons. But all of those are just different coordinates within the overall object space. There is no ability to switch this to world or any other thing. Let's see a quick demonstration with our texture here of how this all winds up working out for us. We have, of course, for many things, coordinate inputs like this on the procedural texture, where of course we're able to reposition a texture on a surface. And this sticks, of course, because these coordinates are given in the object space. If we hit world coordinates, then of course we get a different behavior. The texture is fixed in the overall world space, and so moving the item moves it through the texture. In this case, moving it on the Z, the texture appears to be flowing off towards us here. Now I can also, of course, do stuff like grab a null, get its item info and position, plug that into the texture's position input, and as I move the null, obviously the texture goes with it. However, here's the interesting thing: if I move the ball, it doesn't. Reason why is because I'm grabbing the null's value there in its parent space, which just happens to be the scene space, world space here, and that value is still 0, 0, 0, because the null has not moved. Therefore, the position going in here, irrespective of the ball movement, remains at 0, 0, 0. And the texture gets projected in the ball's local space. However, here's something different. If I change the item info to the ball, then just taking its parent position still, if I move it on the Z, what we see is that the texture flows again. But this time it's flowing the opposite direction. This is because the ball's input Z, which has gone up 600 millimeters there, has pushed the texture 600 millimeters over the ball, because it's pushed it in the ball's local space. Were of course the ball to be a child of the null, then you could move the null and you wouldn't get this effect until you move the ball within this new parent space. However, of course, if we were taking the world position of the ball there, then moving the null would still have the same effect. What this really shows is how the data is flowing through the network. I've said it before and I will say it again: follow the numbers. And in the case of things like positions and rotations, so of course primarily dealing with vectors here, the numbers are gauged against a specific reference space, namely either the parent space or the world space. It is also possible, though, to either start constructing new frames of reference or just grabbing certain components from a given reference frame. Let's say I get a regular vector subtract here. We're still on my ball. I'm going to take its world position and subtract from that its local position and put that into the position of the texture. By doing this, I've essentially created a new vector space which produces a whole new behavior across this parent-child space relationship. So moving our null here, which is the parent, has exactly the same effect as were we just to have the world position by itself plugged in. But moving the ball results in the texture sticking Of course, were I just plugged straight in on world position, then moving the ball would also cause the texture to move, as its world position is a combination of its parent motion plus its own motion. By subtracting its own motion, I've created a new reference space for the texture that is local to the ball, but also relative to the world. Now that's a very simple example, and you can get into an awful lot of complex multi-layered transforms depending on how complicated your scene is, and of course all the variables that you're trying to cross-match or add up and so on. And we won't be going into too much heavy such detail throughout these tutorials, but we will see a number of situations where little tricks like this do come into play, most especially when dealing with motions, because motions and animation really is happening here in the space. The majority of the time, textures we will just want to be having in the object local space. To begin explaining this, I want to visit back on the example that we looked at in the vectors video, where we were targeting the camera at the null. So here we have a terribly poorly drawn grid and a couple of points on it in space, and we want one to be targeting the other. As we saw, their rotations by default, their forwards, are pointing straight out here, as it were. Now, of course, we saw in the video we used subtraction of their positions to do this, and we saw that when it came to thinking about it, you really could just think of taking one length and sort of chopping it off the other to get the one between them. As a rough picture in your head, it sort of works. I want to look at the numbers a little bit here, simply because I want to be able to illustrate quite clearly how that really gets derived, because it's important relative to this whole space thing. So let's just grab the approximate values here from my abysmal grid. I'm going to say that this upper point here, that's about 1.2, 2, okay, for x and y, whereas the other is about 0.8 and of course 1. So of course I do the old subtract in between there, and what I get left with is 0.4 and 1, which would be, roughly, that's half, so this is about 0.4, 1, somewhere around there-ish. How does this work out? Because of course this position is here, it's not between or anything else, these 2 points, and of course it is being drawn from the origin. The vector we think of as a little arrow in this sense, and so our vector result is actually this, not anything here at all. The vector in space, in this grid space, exists over here. It's coming from the origin. The point to it is the angle of turn, because when this vector was applied to our item here that we want to do the targeting, we input it as an amount of turn, and that turn of course comes from the object's pivot point, which is here. If we turn it by that amount, then the direction that we get is pointing at the other item. What we have is this vector here and this vector that we created from the subtraction are parallel. They're at different points in space, but it's how one is getting applied to the actual destination item itself. Now, this also brings up something else interesting when we were talking about world and so forth. If either of these objects were to have a parent null, then either could still be repositioned somewhere else entirely on the grid, and the target behavior would have worked, because we would simply be grabbing the coordinates from the world spaces, grabbing them like we have done here as if they have no parent. The world is the reference frame for each of the 2 vectors, and that will always give us the correct amount of world rotation between them, and when we apply that to a local input we get the correct result. The difference would be if the item being controlled, so doing the targeting, had a parent, and that parent were to be rotated. What happens, of course, we see here, when the parent is rotated, is that item 0, its forward, relative to the world here, gets turned with it. Doing this method gives us the vector that would be relative to this forward here, so an angle of that amount that we see here. But because we apply it in local space, that angle would be taken at the pivot and we would have had an incorrect result. So when we are here in the nodal motion editor, we have to remember that at all times the input to the nodal motion is parent space. The values that you input to these connections will move or rotate the object in its own parent space. As such, when you do look at items themselves, you'll want to be careful of which space you are grabbing them in to make sure that you get the right lookup. This, as we just saw, goes doubly important for rotations. The standard rotation output here is of course the rotation in heading pitch bank in the parent space. If you want world rotation, then you have to take it as a matrix from the right up and forward. And again, as we saw with the position example on the sphere's texture here, you can add, subtract, or whatever these different spaces from one another to grab your vector in the correct reference space and make your parent relative rotations and positions correctly line up with the positions, rotations of other things in other spaces. Let us then, for proper clarity, take a look at this in Lightwave. We see here the setup with the camera and light from the vectors video, and what I'm doing is grabbing the world position of both items, so any parenting makes no difference and the target behavior works just fine, and of course continues to work fine whether it's the parent that's moved or of course the camera itself. The problem of course becomes very clear if we take the camera's parent item though and begin to rotate it, because of course this vector that we're finding from here takes no account of the parent's rotation at all. The fix for this is simply another subtraction, but this time on the rotations. What is happening in effect is that the parent's rotation is being added onto the rotation here that's being found from this vector. So we basically just need to subtract it. So we find ourselves effectively wanting something like this, where we take that parent item, take its rotation, and simply subtract it from our result here. So we can add on degrees in heading, which take the camera with it, but then subtract those same number of degrees, making the camera effectively turn back, and it appears thus to stay still. However, if we wobble this null around, we'll find that actually all is not happy. There's a reason for this, and it has to do with the fact that we're dealing with Euler ordered rotations. This subtract node does not take care of them properly. In the section of node-specific videos, where we introduce a lot of the vector operators, we'll talk about this stuff in more detail. But for here, an obvious way to do the subtraction is also to add the opposite, or the negative, or the inverse. So we could attempt to deal with this by grabbing the rotation, multiplying it by -1 to invert it, and then use the actual HPB add node to sort of perform this subtraction. So we're adding the negative rather than subtracting the positive. And whilst this does work, like previous on some axes, such as the heading, when we roll around we've got exactly the same problem. Again, it's because this isn't HPB specific. Let us just take a moment to assume, however, that we did have a proper subtract node or multiply node for Euler rotations and this whole thing was working. For the sake of example, we can say it's working on the heading here, possibly check it out in view 2, like this. With this kind of setup working, what we still see happens is the result if we add another parent into the hierarchy. Of course, the rotations and positions of our cam null there still support the target behavior, but those on this new null, of course, do not. The solution, of course, is that like the position, what we want to do is take the world value and kill that off. Our vector, which we are finding here, is still always getting the correct result for camera to light. It is, of course, if we imagine being drawn from the origin here of world, it is parallel to that direction. Irrespective of what's been happening with this whole system, the vector that now runs between these two is still outputting here correctly up there. So it's by doing our comparisons in the world space that we can get round these parent space issues. And the way to grab the world rotations, as we saw in the vectors video, is via the rotations matrix for right, up and forward. If we grab cam and go to the position tool and look at its local axis, we see that its local forward is pointing this way. We can get its world rotation. So by subtracting its world rotation from this figured out world rotation, we will get an answer that is correct within this local space, or in this parent space I should say, because of course cam null is the camera's parent. The inverse of the world rotation was the right up and forward, which is what I want to get since I still can't subtract. So by taking that fella and popping him in instead, this is essentially the right up forward times -1. We can see that any rotation here is working just fine, and we're not losing target on the light. If I go to the camera view so as we can actually see this, then of course no matter what I'm moving or rotating nor how, I'm always getting the correct angle of view to the light. There we have it, look at my camera all the way over there. The other thing we can then realise at this point is that actually the camera itself, its local space is right under its parent space, and of course it still has world vectors for right up and forward. So the truth is, I could just have taken the ones directly from the camera itself and it would have made absolutely no difference. I would still have the exact same correct behaviour here. The one thing you may have noticed, of course, is that our camera is twisted here on its bank. Just to let you see, if we disable the nodal motion and just use the regular target item, we still get a similar effect. This, of course, is because we're not defining a pole or an up vector. Turn that off, go back to nodal, and we can see that I've got a vector here, which is just a constant up, 0, 1, 0, and by popping that into the up here, then that means that my camera is always aligned directly up, irrespective of what else is happening. And again, we can make another demonstration of this space thing by putting in a null here, whose position we'll call to be our up vector. Even though it's over here, the camera is aligning its up parallel to it. And so when the camera is oriented this way, as we see like this, then obviously the x-axis of this null is controlling the bank there. The z does a tiny bit, but only because this camera isn't completely orthogonal on the axis as I have it. But what we notice is if we come round the other way, then now moving our up on the x is having basically no real effect, and it is instead the z now to which the camera, of course, aligns there, because the alignment is parallel from the space taken to the input space, because of course what is being matched is the alignment. If up were instead to be a child of the cam null, then what we see of course is a totally different result, whereby the camera does not appear to be aligning to this vector in any normal way, except of course that it is. It's performing exactly like it did before. When it is at 0, 1, 0, we get direct up alignment. And in this case, with the camera pointing this way, it was the z that affected us before when we were a scene child, and it still is now. It's because of the space that we're taking it from. And the reason why 1 in this space is over there is of course because this cam null has been rotated off somewhere. Were you to be back nicely at 0, and of course your parent also, which I can lose realistically for the sake of these further demonstrations here. So were you in fact at a full 0, then of course our pole would be up there and we'd swing around just like this. But of course rotating that cam null, even though it takes the pole with it, doesn't change the pole's value. So that does not change the up vector of our camera. Some of you may think, haha, the answer is the world position, right? Totally wrong. Because of course now the vector is essentially being drawn to the origin again, and we can see that that is what our camera is aligning parallel to. No, what we need to find is this vector drawn by this line. And so what we do is mimic what we did here. We take the up null's world position, the cam null's world position, subtract them, and this becomes our up. And as we can see, it works exactly as expected. And when we rotate this thing around, the camera bank keeps up, though the targeting still works. And what these all put together demonstrate pretty well is how all of these spaces stack up and how we manage them. The first trick is world, getting world positions, getting world rotations. By doing that, you can take all the vectors into a singular space, the world space, and do your necessary comparisons and get the correct results out. You've then got the space where you apply them. If you've just done something simple like this initial position, or of course this rotation, which is more or less the same thing, just done with a couple extra nodes to pull out the proper world rotation and sort of subtract it, But when we're making these vectors in the first place, we can make them within given spaces, which is what these do. I'm looking at the world position, but the vector I get out is equal to the direction as it would be in this parent space, specifically this item space. So I get a vector from and to. And all of this is done so that we get something that aligns properly to the destination space, which is of course the regular old coordinate input for our item. Now at this point, of course, I appreciate we're starting to get into a lot more detail of these specific things. And of course I realise a lot of you may think, what does this have to do with work in general? It seems like an awful lot of it is related just to motions, rigging and that sort of thing. But of course, as we've seen, one of the advantages of Nodal is that you can start to bring some of those kinds of workflows and control systems into the way that you set up and control and animate textures. So that's all good stuff to know. Plus, of course, there's plenty of other instances, such as instances, which we scatter around a terrain and we're interested in their position and their rotation, blending different colours between them and so on. This sort of stuff comes in very useful there as well. But any which way round, at this point, we're going to move on, because rightly or wrongly to continue would more or less require just lots and lots and lots of additional examples. What about this in this space, that in that space, this kind of setup, that kind of setup? And there's just too many possibilities in this whole raft of potential scenes and situations. And so an awful lot of this you will just have to go through, try things, practice. Just keep your eyes open and try and figure them out for yourselves as you go along. But you will see throughout the course of these tutorials that when we are dealing with motions and rotations and anything else, lots of the time with vectors, we will make reference to this whole issue of spaces to explain the flow of data that we're constructing, how it works, why it works, to help you further get clearer ideas of how to think your way through it for yourself when you're confronted with your own individual specific scene problems to find solutions to. And that really wraps up this whole introduction to the spaces in the node editor. Obviously we could talk about things like the displacement node editor, but this is very much like surfacing. A displacement is like a surface that outputs a positional value rather than a color value at a given point on the mesh, that's all. And so again, this is surface space, object space. And you'll find that pretty much any incarnation of the node editor falls into that same way of working. Were you perhaps using something like DP's node image filter, then of course the render buffer has a space as well, which is done as integer pixel counts, motion X and Y within the frame space. So hopefully that's introduced you to some of the issues that you will find yourself confronting in node editor when dealing with things in different spaces, shown you why these things occur, so as hopefully you can begin to think your ways around them and find solutions to them.